Hey guys, so I'm going to do a simple tutorial on how to use the MATLAB PDE modeler in order to solve different partial differential equations. So this one we're going to model like a circular blood vessel, and you can start by drawing the shapes, and you could go into draw and select like different shapes. In this case I already have my circles here. And notice how every time you draw shapes and you overlap them, they're going to be together. However, if you go up here and specify that you want to do, for example, E2 minus E1, this is the bigger one minus the smaller one, you're going to get just this boundary here, which closely resembles like the blood vessel. And for this, you want to start off with defining which function you would like to use. In this case, we are studying the diffusion of like a certain drug injected into the blood vessel. And so we select the diffusion here, and this is just specifying like the boundary conditions. So for example, like for the outer boundary, we're going to say that our concentration here is just going to be 1. And we're going to do that for all of these boundaries here in the outer circle. However, for the inner circle, our initial concentration is going to be 2. And that way we're going to see like the actual modeling of the concentration gradient. And so when we go into PDE, you also want to specify your D coefficient, which is just going to be 1, as well as we're going to specify the solution output as in terms of concentration itself, which is the variable U. Because since MATLAB outputs that solution in terms of x and y coordinates, we just want to have it together complete as 1. So once you've specified those, we can go ahead and, let's see. So yeah, once you already established your boundary conditions, notice how we kept them as the Dirichlet. I don't know how to pronounce that, but yeah. So then we're going to go ahead and initiate our mesh. And this is just basically going to resemble like, I guess the particle like pathways, or I don't even know, but these triangles are going to tell you like how the concentration is going to be done. And you could refine it if you want or make it less refined. I feel like the more refined it is, the better results you're going to have. And so once you have done that, you just click the equals button. That's going to solve the PDEs for you. And there you go. That's the concentration gradient, as you could see with the color bar. You can also modify this, plot it in terms of different things, flux, other things, as well as change the color. So if you wanted like this one, it would change it to like this. I don't really like that. I'm just going to keep it as cool because it's pretty cool. So there you go. However, another part we can do is, let's see. So once you already have your established model, we can go ahead and export the coordinates. So go into mesh, go into export mesh, and this is just going to export like all of your coordinates in terms of points, edges, and triangles. So we're just going to go ahead and leave those variables the same. And we're also going to make sure we have the nonlinear check enabled, and the Jacobian method is going to be full. This is what's going to help us get like the full solution. So then once you've done that, we go ahead and export the solution. We could just leave it in terms of U, which is just the concentration. And okay, we already exported it. So then we're going to go into here. And in this code, I basically have the diffusion. We're going to plot it in terms of basically the radius points that we found. So the exported P array that we have exported from the points, those are actually going to be like translated into polar coordinates. So this is what this function does. It takes the x and y coordinates of this array and just implements them into the radius. And we're also going to plot this in terms of U, which is our concentration, which we exported previously. And then we just have the x and y labels in the titles. So then when we go ahead and run this, you're going to see that this is the concentration profile across the vessel. And it's plotted in terms of the polar radius coordinates and concentration. So then we can apply this similarly to maybe like a similar, let's see, like a similar model, but in terms of ellipses. Sorry, I can't talk. But let's see. I already have one modeled here, but let's see. So here we have the same thing, except I modified my ellipse, so I just have the coordinates, like you can alter this, but I just have it set to this axis. You could also, let's see, you could like set your axis limits to whatever you would like. I just set it here because it's like a nice indication we can see what's going on. And same thing, so like we have our two circles, or ellipses rather, and notice how up here it's E3 minus E4 because you just want this portion. So then you're going to go ahead, set your boundary conditions. In this case, we're going to do the same thing. So the inner radius is going to have a concentration of 2. And the outer one is going to be just 1. So you're just going to see like the gradient across. And we're also in the diffusion segment as well. We also have it in terms of U. Everything's the same pretty much. Also make sure that your parameters are set to Jacobian. And then we're gonna go ahead and initialize the mesh. That's like really refined, so I'm just gonna take it down a notch, like maybe, yeah, this is fine. Okay, so then we're just gonna do the same thing. We're gonna press solve. You get this nice figure here, to like a scale as well. And we're gonna do the same thing. So we're gonna go into mesh, export mesh. I'm gonna label these as maybe like uppercase P, just so you could see a variation from the other one. And we're also going to export our solution. I'm just gonna put it as like uppercase U, just for variation. Now those are gonna be exported here. Now for part 2, just go ahead, delete that. And I'll just like comment this out so it doesn't mess us up. But here's basically the code. Oops. Let's see. Okay, so this is the code. For the second portion, we have the same thing except I changed, notice, the uppercase P for our new updated points and then uppercase U for our updated solutions. Same thing, titles. And we're gonna go ahead and run this. And now this is our concentration profile for the elliptical blood vessel now. So it's pretty cool. And finally, for the third portion of this tutorial, we're just going to do a kind of a different one. And this is going to be in terms of a steady state diffusion across the membrane. So I'm going to go ahead and open it. And here you can see as well. So this is a little bit different because it's in terms of a rectangle, but again, like you could come in here and draw and like set all of your boundaries and stuff, make your own shape. So let's see, we're actually gonna alter some of the boundaries. So for instance, like since this is the membrane, it's going this way horizontally, the concentration gradient. So we could set these boundaries actually to Newman and have them just be 0, because we're kind of looking at the horizontal direction. Whereas, for example, the vertical boundaries, we're going to have the concentration go from 2 to 1. So the initial one's going to be 2, and then this one's just going to be 1. And 0. But it's going to help us like model the flux and stuff. So again, we're going to initialize our mesh, make it like super refined for better results. And let's see. We're gonna have our coefficient just be 1 again, in terms of U again, same stuff. And this time I'm not gonna plot it through MATLAB, I'm just gonna show you the solution. So we're gonna go ahead, solve it, and here you go. So as you can see, the concentration initially is at 2 and it just kind of spreads evenly because it's steady state one-dimensional. I like the jet color because you can see it better, but there's a lot of options you can utilize. I don't really like that, so I'm just gonna keep it as jet. But yeah, that's basically how you can model, realistic like functions and stuff in the real world using MATLAB's PDE modeler. This is a really cool tool. Sorry, I can't stop. And I really recommend it to people who are especially like introduced to coding and stuff recently, because then you can do a lot with this. So I hope you guys enjoyed. So thanks again for watching. I hope you learned something. If not, oh well, but thank you.